Okay. Yes, we can certainly do that. D on the homework. So that's the one with the adding the alkynyl anion to the carbonyl group.
Yeah.
The acetone. Okay. All right. So when you make your alkynyl anion, what we can do an SN2 reaction, we know, and we talked about it doing an E2 reaction if it's a tertiary halide. The new reaction that it can undergo is that it can also do is it can add to a carbonyl group. Now we're gonna talk about this next week, not with an alkynyl anion, but just with a regular C-. And so they're kind of we're introducing this now, and we're going to do a lot of these next week in making alcohols. So what happens is that if you remember the carbonyl group, the carbon is delta plus and the oxygen is delta minus. And that comes from its polar covalent bond. So that makes the carbonyl carbon electrophilic because it's slightly positive. The minus charge will then come in and attack the carbon to form a carbon-oxygen bond, but if I stop there, that carbon's got 5 bonds. So then what happens is the pair of electrons goes to the oxygen, which already has 2 lone pairs. But in terms of electronegativity, this works fine, because the oxygen is more electronegative than carbon, and so it wants the negative charge. So you're going to get then the carbon-carbon bond being formed with the O- as the final product. Now, the O- isn't going to be the final product, because we don't make products with negative charges. We always make them with neutral. So what we're then going to do is we're then going to add H plus to this so that the O- can be protonated to form the final alcohol product. So this is basically addition to a carbonyl group. It might be called in your book acyl addition, because that's what another name for a carbonyl group is. Now, the reason this is a 2-step reaction. So step 1 is to react the alkynyl anion with the carbonyl. That's step 1. And then in a distinctly separate step, we add the acid. Because if I had the acid present, it would protonate the alkynyl anion and kill it, so that there would be no reaction. So I have to add the alkynyl anion, and then after the reaction's over, bless you, then I add acid. And that gives me the final alcohol product. Now, what was throwing people was it was H plus H2O. Again, I can't go to the stockroom and just get H plus. It has to be dissolved in something. And so what we're going to find is in the reactions that we do next week, there's always going to be 2 steps. There's going to be adding the negative carbon, the carbanion, that's a negatively charged carbon, to the carbonyl, and then H plus H2O step after it's over to protonate the alkoxide to make the alcohol. So that's kind of setting. And if you wanted to see the video for this, it's in Monday's lecture video. You could fast forward to it. But that's how this works. And then for your transition states, when you're writing transition states, remember that when you're forming a bond, there's a dotted line, and when you're breaking a bond, there's a dotted line. So for instance, for the first step, we would have, since we're breaking the carbon-oxygen bond, we'd have a dotted line there. And then we would have a dotted line to the alkynyl anion. And then we average our charges from the reactant to the product. So the C minus, and over here it's neutral or 0. So the average of minus and minus 1 and 0 is a delta minus. And then for oxygen, a 0 and a minus 1 makes it a delta minus. So the negative charge is being transferred from the carbon to the oxygen. I'm breaking the double bond, I'm making the carbon-carbon bond. And for simply protonating the OH, there's going to be a dotted line between the O and the H. Oxygen delta minus, hydrogen delta plus. So that's another reaction of an alkynyl anion, is to add it to a carbonyl. So E is the alkynyl anion plus the cyclohexane. Okay. Okay, so in all the reactions, you had to make the alkynyl anion first. So in this case, when I'm reacting the alkynyl anion with the halide, what kind of halide is this? Primary, secondary, or tertiary? It's tertiary. So what kind of reaction will this be? What mechanism? It'll have to be E2. Because the tertiary halides cannot undergo SN1, cannot undergo SN2. Now, a couple people said, could it go SN1? Maybe. When we have remember, this is a really strong nucleophile / base. It has the dual personality because it's a C minus. So when we have a strong nucleophile and a base, it wants to act as a nucleophile first. And when it can't, it'll then turn around and act as a base. So in this case, the tertiary halide cannot undergo SN2. Maybe there's enough time for it to lose the chloride and then have the C minus come in and add so that it's SN1, but most likely that's not going to happen. The minute that this cannot do SN2, it's going to turn around because it's such a strong base, and it's going to deprotonate a beta hydrogen. So your choices and this is the first base that we've had like this. Right? Last semester in my class, we had two strong bases that always did E2. NH2 minus and tertiary butoxide. Small, sterically hindered. Those two bases always did nothing but E2. They never did SN2. So this is a new kind of base that can do both. So if there's a primary or secondary halide, it's going to do SN2. If it's tertiary, it's going to do E2. And we'll have a couple more of these that we'll add on. I think including next week or early the week after. So that's all this can do is SN2 or E2. There really isn't enough time to lose the chloride. It's going to do something immediately. So we're looking at an E2 reaction. So this is going to seem like deja vu from last semester. But when we do E2, what's our first step?
Find the beta hydrogens.
Find the beta hydrogens. And in order to find the beta hydrogens, we first need to find the alpha carbon. So the alpha carbon's attached to the leaving group. The beta carbons are attached to it, and there's 3 beta carbons. And then we look at the beta hydrogens. And then the second thing we have to make sure, since this is E2, is that those hydrogens are antiperiplanar, that they can go into the antiperiplanar geometry. In this case, they all can. Because I didn't give you a stereochemistry of whether the chlorine was above or below the plane of the ring, and it doesn't matter because there's 2 hydrogens on each of the ring positions, and with the CH3 there's free rotation to rotate any of those 3 hydrogens into the antiperiplanar geometry. Right? And remember, those are the steps we have to do. We have to take it that way. So now we look at the base and we say, is this base going to give us, is it sterically hindered so that it'll remove the hydrogen that is most accessible, or is it small so that it gives us the most stable double bond? And what we've been saying is that the alkynes are really not sterically hindered, and so we're going to treat them like NH2 minus. So we're going to remove the beta hydrogens to form the most stable product. So that's going to be either these ones or those ones. Does it matter? No, because you get the same product either way. So my C minus is going to come in, grab a beta hydrogen. That beta hydrogen, the pair of electrons is going to go to form the double bond, the chlorine is going to leave. So we're going to end up with a double bond there, and the methyl group there, plus the protonated alkynyl anion, just the alkyne. So that's the difficulty. That's the thing we have to take into account here. Primary, secondary, alkyl halide, SN2. Tertiary, E2. Any other questions about anything?
So for the front, how do you know if you're making terminal versus
That was like in problem 2, right?
yeah.
So if we have a situation, if we have like a geminal dibromide where with the geminal dibromide, remember we're going to do double E2. So that means we actually are going to have the alpha carbon twice. So this is going to be the alpha carbon in both of those elimination reactions, which means we have 2 beta carbons and 2 sets of beta hydrogens. So we could actually, from this molecule, we could form the internal triple bond. Or we could form the terminal, depending on whether we wanted to deprotonate hydrogens A or hydrogens B. So if we deprotonate the 2 hydrogens A, we're going to get the triple bond in an internal position. If we deprotonate the 2 hydrogens here at the B position, we're going to get the terminal one. So this is going to depend on our choice of base. And we're using NH2 minus for this. So NH2 minus is a small base. It forms the double bond, and in this case it's going to form the triple bond that is most stable, which means most substituted. So NH2 minus is going to form the internal triple bond, analogous to how it formed the most stable double bond. Now you might say, well, how would you get the terminal one? And I don't remember if I did this in this class, but let's think about, I need a sterically hindered base that's strong enough to do both E2s.
Can you use that SIA?
Close. The SIA2BH is actually, that's what we use for anti-Markovnikov addition of H and OH. But it's exactly the same principle. When I'm doing this, I'm trying to add H and OH to the triple bond, and I would like to add the boron to the end, and a BH3 just isn't big enough to differentiate in a linear triple bond. So I'd get probably a mixture of the two, of boron adding to each of these two carbons. When the boron adds, remember the H2O2 replaces it with an OH, and then you do the tautomerization. But it's the same principle. I took BH3 and I added this. The name of this is just, it violates all the IUPAC rules because it's a secondary isoamyl group. Amyl equals pentyl because amyl's the old term for pentyl, and secondary isoamyl is just, there's no common name for that. But it's a very sterically hindered group. So the idea here is I know an N minus. I know the N minus will deprotonate in the second step. So let's make the N minus sterically hindered. And I could use this secondary isoamyl group, but what's commonly done is we just add two isopropyl groups, and we make this what's called diisopropyl amide. And if you really wanted to do this in the lab, you'd go to the catalog, and what you would find is that this is lithium diisopropyl amide, which is LDA. So the N minus is strong enough to do both eliminations, but now what I've done is I've turned the tables on it and said, okay, let's use the sterically hindered base so that it forces the B hydrogens to be the only ones that are removed. So I do have control over forming the internal and the terminal. I would just choose two different bases. And this one we might have talked about last semester. I mean, our what we would say is, okay, how about tertiary butoxide? Tertiary butoxide will do the first elimination. It's going to need help on the second elimination because it's not that strong of a base. But the N minus is. So if we use a diisopropyl amide, it would do that. The SIA2 is a secondary isoamyl. So this is the iso 1, 2, 3, 4, 5. So this is like an isopentyl group, but the attachment point is secondary. It is a completely made up common name that just violates everything. And so your boron would actually, you would actually have two of those groups, and that's going to force the boron to add to the end of the triple bond. And it's not even the one that I think if you went to try and buy this from the catalog. I don't think they sell it. They put the boron actually in a ring to make it. I think it's called 9 BBN. But same principle. We're using this when there's not enough steric hindrance in the reactant, or in our molecule we're reacting, then we take our reagent and we make it sterically hindered to force a choice. Okay. So that's how we could form. So in the homework problem I gave you, we were doing NH2 minus. So that means you're going to form the triple bond that's most stable. What else? And I know you're going, well, he's just going over the homework problems. I won't always do this. But remember, the homework problems are low stakes. And the idea here is to get that this is what's telling you what you don't know and that you need to ask questions about. And I always have the option of making another homework assignment, building on some of these for next week. I'm not going to for Wednesday. The only thing that's due on Wednesday is that long, those review problems. But after that, I could put some of these homework problems. I could give you additional ones. And there's always the practice problems that are in the folder as well. Anything else? In mopping up the reactions of alkynes, we had all of the additions. So HBr and peroxide to do anti-Markovnikov, Br2, so we can add 2 Brs or we can add a total of 4 Brs. There was the idea of the oxidation, which I'll just quickly go back through here and say, last semester when we did our oxidation, we did our cleavage. We used O3. We did ozonolysis, or we used KMNO4, acid, and heat. Remember, the triangle indicates heat. Those were the ways that we cleaved the double bond. And last semester, when we cleaved a double bond, we ended up erasing the double bond and putting in our carbonyl groups, converting them to carbonyl groups. That's how they became That's how it became oxidized. Oxidation, gain of oxygen in organic molecules. And then our only question is whether when we had an aldehyde that resulted from that, did that aldehyde get oxidized to a carboxylic acid? And that was the case with KMNO4 because it was strong enough to oxidize an aldehyde to a carboxylic acid. And with ozone H2O2, you would also then oxidize any aldehydes that you get to a carboxylic acid. And if you don't quite remember that, you might want to go back. And I need to add the people that don't have access to last semester's Canvas. I will add you today to the Canvas 1, to the Organic 1 Canvas site, so that you can go back, and if you wanted to watch the videos, all my videos are in my YouTube channel. So if you just search my name and Chemistry 221, 222, that's how you get there. I don't think they're anywhere else. They were for a while. Somebody hijacked them and made their own site. which I didn't honestly care about until they started monetizing it. And then I said, yeah, that's a violation of my intellectual property rights, so I'm going to sick the university attorneys on you unless you take it down. And they finally took it down. They had it better organized. Somebody from another school's like, can you organize these according to topics and not dates? Well, yeah, if you were at the school. I don't have time to help somebody else from another school. No. It's a little more difficult, but then you just fast forward through it and see what the topics are. So that's where all the videos are, but I will add those of you to the first semester today. It's been a hectic week. So that's what we did last semester to cleave. I think cleaving triple bonds is actually easier because ozone won't cut it. Ozone's not strong enough. So if you want to cleave a triple bond, you got to use the harshest reagent possible, which is the KMNO4. So when you cleave the triple bond, then you do the same thing. You erase the triple bond, and now we put in our carbonyls. But we don't have to worry about this. Is it a carboxylic acid or is it an aldehyde? Because there's no hydrogens there. We cleave the triple bond. So they automatically become carboxylic acids. So we automatically cleave the triple bond to make 2 carboxylic acids. So there's no question about, there's no issue of, well, do I oxidize the aldehyde or not? Alexa?
How can you just erase the triple bond?
Well, because that's in essence what we're doing. We're cleaving the bond. And so when we cleave it, in real life, the triple bond's just not disappearing. But if we want to write the products, that's a way we can do it. So basically, when I cleave the triple bond, I just erase it, and then it's being replaced with 2 carboxylic acids. So it's just kind of a methodology to write the final product. The KMNO4 is probably going to come in, bond through the triple bond, then break it apart. But the mechanism last semester was something I just showed you. It wasn't something you're responsible for. I'm not even going to show you this one. So in essence, that's what we're doing. When we cleave a bond, just erase the bond, and then something's got to go there. So that was the oxidation part of the triple bond. And I don't think in the book they add like 4 OHs to the triple bond. I don't think they do that reaction. So then the other thing is reduction of the triple bond. So when we talk about reductions, I know at least in my video that there are 3 reactions for reducing alkynes. And remember that the whole idea here, particularly this semester, is we're thinking about having a big toolbox of reactions that we can convert one functional group into another. And we'd like to do it where there's possibility of one product or another product. We'd like reagents to do both. So for instance, we know that we can do Markovnikov addition and we can do anti-Markovnikov addition for different reagents. So that gives us the ability to add H and OH Markovnikov and switch the positions of the H and the OH or the HBr. So when we reduce a triple bond, we can reduce it totally down to an alkane. We can reduce it then, if I want to stop at an alkene. Of course, the problem there is am I going to get the cis-alkene or am I going to get the trans-alkene? And ideally, I would like a reagent that lets me make both the cis or the trans-alkene. And then, of course, the alkane. So these were the three reduction reactions that we had for alkynes. And the reasoning for these, if you think about, well, what did we use last semester to reduce alkenes? We used H2 and platinum or palladium metal. What you have to realize is I don't have any control over the hydrogen. I usually use excess hydrogen in this reaction. Nobody ever determines exactly 1 mole equivalent of H2. They always use excess. So the problem here is that when the hydrogen adds to the triple bond to make the double bond, that double bond then reacts with hydrogen and palladium to go all the way down to the alkane. And you can't control it. If I use just 1 mole equivalent of H2, I would get a mixture of alkane, alkene, and then unreacted alkyne. So I just use excess and force it all the way to alkane. And so that's what will happen if you use pure strength palladium and platinum. And then somebody said, hey, I want to stop at the alkene. So how do I do that? And then they came up with the idea, well, bless you, if palladium and platinum is a really, really good catalyst or really active catalyst, can I somehow poison it so that it isn't as reactive and so that it won't reduce a double bond? And so they did that. And the person who did that was Lindlar. It's called the Lindlar catalyst. Lindlar. It's called the Lindlar catalyst. And the Lindlar catalyst is like palladium that's coated with barium and this aromatic compound called naphthalene. I think it's like barium oxide. Anyway, it's a very specific set of reagents that is added to palladium metal, which kind of kills it. It makes it less reactive so that it will not reduce the double bond, David.
But you still need the H2.
Yes, you still need H2, but what I've done is I've modified the catalyst. And actually, the technical term is I have poisoned the catalyst. Intentionally, so that it's not as reactive and it won't react with the double bond. So the hydrogen still adds cis, which it did with alkenes, but now with the poisoned Lindlar catalyst, the double bond won't react, so it stays. And I'm sure there's other variations of this. I think the Lindlar catalyst is probably patented, or it was at some point. Sometimes catalysts, like in refineries, they're using catalysts to take the long-chained hydrocarbons of crude oil and breaking them up to make smaller chains that we can make gasoline out of. And those catalysts get poisoned, but not intentionally. They get poisoned by the sulfur that's in the crude oil. And so trying to keep metal catalysts like this from getting poisoned is a big problem in refining. It'd be best if we could just take that, because the cost of palladium or platinum, those are very expensive, be like gold catalyst. If we could regenerate them somehow, that would be more cost effective. So that's what the Lindlar catalyst is. I know the Lindlar catalyst was in my notes. I can't remember if it was in the book or not. But then the question is, okay, so I can make the cis, can I make the trans? And when you make the trans, you use sodium metal in liquid ammonia. And this is what I said last time. I wanted to make sure that these two reagents are actually, this reagent is different than NaNH2 because NaNH2 is just NH2 minus. That's amide with a counterion. Right? Because we normally kind of have been ignoring the counterions. I do that because they end up everywhere. Like they end up, the worst place they've ever shown up is inside of a cyclohexane ring. I have no idea how they got there. But there's like a sodium or potassium just stuck inside the cyclohexane ring. That's not where it's going. It's just the counterion. So we usually write NH2 minus. I can't go to the stockroom and get NH2 minus. I gotta get sodium or potassium or lithium. I've got to get a counterion for that. And in this class, they all react the same. In real life, they don't. But we're not going to go into that complexity. So sodium metal and liquid ammonia is a different reagent than NaNH2. So what happens in this case is, and I think I had the video, or I had the scheme, this is not a mechanism you're responsible for, but it helps explain the reaction. What happens is that whenever you take an alkali metal, remember the sodium has one unpaired electron. When you dissolve that, when you add that piece of sodium metal to liquefied ammonia, and then you have to ask the question, okay, what's liquefied ammonia? How do you liquefy ammonia? Well, it turns out that if you use like dry ice, which is solid carbon dioxide, ammonia liquefies at like minus 20 or so degrees. So you actually can take and have a round bottom flask like we use in lab, but then for the condenser, it's not water, it's kind of a test tube where you put isopropyl alcohol, rubbing alcohol, and dry ice, and that creates a minus 78 degree situation. And then as you bring the gas in, it liquefies and drips down into the round bottom, which hopefully you have in dry ice as well. So you can actually create a round bottom that's got liquefied ammonia as a solvent. And you have to keep it dry, you have to keep it really cold, because if it warms up, all of a sudden that liquid becomes gas and the whole thing explodes because it can't handle the pressure change. So you make liquefied ammonia, you add a drop of sodium metal to it, and it turns bright blue. Not like North Carolina blue, because remember, North Carolina blue is bad. It's the more of the other institution blue that's up the road that I went to and had season tickets for. The dark blue. But that dark blue is an unsolvated electron. So when you add sodium metal to liquefied ammonia, the electron becomes like free. And so when you have free electrons floating around, that is the best reducer you can have. You could think about, well, maybe we use a battery and we use a circuit to push a free electron in. This was pre-batteries. So this allowed us to get a free electron. And what happens is that free electron adds to one of these carbons, and then the pair of electrons moves to that carbon. So actually that one unpaired electron should have a fishhook because it's one electron. So it adds to one of the carbons, and then still can't violate the octet rule. I've got to break the carbon triple bond. So what I end up doing is I end up forming then one carbon has a lone pair on it, and the other carbon has an unpaired electron. And remember that electrons are just big clouds of electron density. So when you add that solvated electron to the triple bond, it forces those two clouds to be trans. They can't be cis because that would be two big clouds of negative charge repelling each other. So they've got to go trans. And so when they go trans, then this, for instance, is a negative charge. it goes in and grabs the hydrogen from ammonia. So we turn that into a hydrogen. And then the unpaired electron adds to the second carbon, making it a lone pair and another negative charge. And then that one grabs the hydrogen from the solvent as well. So this is the critical intermediate that sets the trans stereochemistry. So again, this isn't a mechanism, and there's both a printed out mechanism as well as I went through that in the video. But this is the reason why it's trans, is because that unpaired electron and then the lone pairs have to be trans because of their big clouds of electron density. Okay. So in reductions, we have the possibility of making all three: alkane, cisalkene, transalkene. And I think that was the last set of reactions in the triple bonds. So, and I haven't given you any homework problems on doing the reactions of triple bonds. I had planned on doing that being due next Wednesday, but that's kind of just piling on. So after the review problems are due next week, then I'll give you an alkyne problem set as homework. Any questions? So today's topic was very much review. If you looked at chapter 14, hopefully it's like, oh, this is all review. And so what was in that what was in the first part of chapter 14? What was Markovnikov addition versus anti-Markovnikov addition? Because it was definitions. What is a stereoselective versus a regioselective versus a stereospecific reaction? And then it also talked about carbocation stability. So our most stable carbocation is tertiary. Our secondary, and then primary carbocations, except in lab with mass spectrometry, we don't write primary carbocations. We can do it in lab, but not here. Because in lab and mass spectrometry, we have a high energy gas phase environment. They can exist, but not in solution. It's a low temperature, low energy environment. And then we get into carbocations like that. Is that a stable carbocation? It's primary. This is called an allylic carbocation. Is it stable? Why?
Resonance.
I can form resonance structures. Whenever the plus charge is next to a double bond, what can I do? I can take this pair of electrons and move it there and write its resonance structure. And so even though it's primary allylic. And so that gives you then two resonance structures, and it's perfectly stable. Be more stable if it was secondary allylic. It would be even more stable if it was tertiary allylic. So we can also have additional stability when the carbocation is next to a double bond. We can also have extra carbocation stability if the carbon is attached to an atom that has lone pairs, like this. Actually, Actually, let me redraw this. Let me put it in context. A tad bit of foreshadowing for next week's spectroscopy. Because I think Dr. Kwan is doing mass spec next week as well. Dr. Simmons and I are on the same page. So I know what she's doing. What we're going to find out next week is this. That if you take a ketone and you do mass spec on it, it's going to cleave by breaking that bond. And when it breaks that bond, it's going to form this carbocation. Now the problem is, that carbon doesn't have a full octet, but it turns out that it's stable because it does have resonance structures. So whenever you have a carbocation next to an oxygen or a nitrogen that has lone pairs, you can take this lone pair and do that with it. You could share that lone pair with the carbon so that you can actually form then a resonance structure where the plus charge can go to the oxygen. So this is actually what's called an acyl carbocation. And it's stable because it can form that resonance structure by taking the lone pairs on the oxygen and sharing it with the carbocation. So this can occur with, that could be an oxygen, could be a nitrogen, might be a sulfur. And so actually that carbocation, that acyl carbocation, is stabilized by resonance. Now, this is one of the weird things because even though this carbon does not have a full octet, this resonance structure is going to probably be a little bit more stable than the one with the oxygen. Simply because who wants the positive charge? The carbon, not the oxygen. But the real structure, remember, is always the hybrid. So another way to stabilize carbocations is by putting lone pairs on the atoms next to the C+. So you can stabilize it by putting a double bond here. You can also stabilize it by putting atoms with lone pairs. This isn't review, but we're going to do this in mass spec when we talk about cleavage, when we talk about the cleavages next week in lab. So that's the reason why we're going to do that, is because it helps you learn and helps reinforce the stabilities of carbocations. The last thing that was in this review was oxidation numbers of carbons. Now, oxidation number of carbon, determining the oxidation number of carbon is different than determining the oxidation number that you learned in general chemistry. And your book has a series of steps. But here's how we could determine the oxidation number of carbon. What we do is we have to know the electronegativities. So when you determine the oxidation number of carbon, it's either carbon keeps the charge or it loses. It either keeps the electron or it loses the electron. This is not a halvesy game. You look at each of the atoms that are attached to the carbon. If that atom is more electronegative, carbon loses the electron to that atom. If that atom is less electronegative, the carbon gets the electron in the bond. So for instance, for carbon in methane, hydrogen is what? More or less electronegative than carbon? Take a guess. Good guess. It's less electronegative. So that means that carbon then picks up one electron. It takes the electron from each of these 4 bonds. So carbon then has a 4- oxidation state. And each of the hydrogens then would be +1 oxidation state. Bless you. So there's no splitting. If the atom that it's attached to is more electronegative, it loses the electron from carbon's end. If it's less electronegative, the carbon gains it. So carbon then has a 4- oxidation state. In this aldehyde, what would happen? Now we got to sum it up. So with the oxygen, what happened? The carbon lost 2. But then with each of the 2 hydrogens, it did what? Sorry. It lost 2, so it'd be +2. And with each one of the hydrogens, it does what? It gains an electron. So it's +2 with the oxygen, it's -1 with each of the 2 hydrogens. That carbon's oxidation state is 0. Like I said, they have the series of 3 steps you use to figure this out. I can simplify that into 1 step. And that is, look at each of the bonds, and the carbon either keeps the electron or it loses it. What happens when you have a carbon-carbon bond? They have the same electronegativity, so there's nothing. So in this case, this carbon would be picking up an electron from hydrogen. It would be losing 2 for the oxygen, and then for the other carbon, it's 0. It's tied. And so this carbon would have a +1 oxidation state, and then this carbon over here would have a 3-. When do we do this? I don't know. We could do this if we wanted to determine if a reaction was oxidation or reduction. But remember, our rule is gain oxygen, oxidation, lose oxygen, reduction, gain hydrogen, reduction, lose hydrogen, oxidation. So that's an easier rule that takes account of this. But that's how we calculate oxidation numbers. Why am I showing it to you? Because when you start doing your problems from chapter 14 in the chapter, then I'm sure they're going to ask you to calculate some oxidation numbers. All right. You can turn in your homework problems, or if you need to keep them till next Wednesday, you could do that. Either one. You can put them here if you're ready to turn them in. The only thing due next Wednesday will be to watch the video that I will I will release this afternoon, and the review problems from 221. If you have any questions, email me, come see me. I'll be around.